Hello, and welcome to an introduction to standard deviation, with me, Mr. McIver, here at the London Central and North West Maths Hub. What is standard deviation? Well, it's another measure of dispersion. This session picks up at exactly the point the last one, an introduction to statistics, ended. If you haven't seen that video already, watch it now, because here's the screen we ended with then. Here are our summary statistics that we should remember from GCSE. Our measures of average are the mode, the median and the mean. You learn all those in lower school, although you probably haven't learned that the mean is often represented by that Greek letter mu. It's a Greek letter M. For measures of dispersion, we've got different measures that go with different averages. So for instance, with the mode, we don't really bother with measures of dispersion, and to be perfectly honest, we don't use the mode much anyway. If we're using the median as our average, we invariably refer to the interquartile range and the range as our key measures of dispersion. And if we're using the mean, we use something new, which up to last week, I hadn't taught you. That is about to change. The measure of dispersion that sits alongside the mean as our average is called the standard deviation, and it is represented by another Greek letter. That strange symbol there is called sigma. So, what on earth is standard deviation? Okay, let's ask a simpler question. What is the deviation of those four numbers? Well, to make sense of that question, you need to ask the deviation from what? And the obvious thing to say is the mean, because that's what we're talking about. Interestingly, in the case of these particular numbers, it wouldn't matter whether you chose the mean or the median, you'd get the same answer. But we're talking about the standard deviation, which goes with the mean, so that's the average we'll be using throughout this presentation. I'm sure you've worked it out already, but I'm going to go through it in detail because I need to explain a little bit of formal notation so that you can understand what comes later. I'm going to work out the mean by adding up my four values and dividing by 4. And of course the answer's 2. Let's just formalize that a little bit. Those numbers there are data points, 1, 1, 3 and 3, we call our x values. Each bit of data is an x. So what we're actually doing is we are adding x1, x2, x3 and x4 and then dividing by 4. In general, if we had n values in our data set, we'd be doing x1, x2 up to xn, adding them all up and dividing by n. And this gives us a formula for the mean that looks like this. Oh, another Greek letter here. That strange-looking E-like symbol is actually a capital sigma or capital Greek S. And we read that algebraic expression as the sum of all the xi's, or add up all the x values, divided by n. Well, that's how you've always worked out the mean. It's nothing new, it's just being written in a slightly odd way. But this is the language of the course. It's also the language used by your calculator, which you'll be using to do the heavy lifting on this work. Once you have done this calculation and got our mean of 2, which is the answer we want in this case, we've got a bit of notation for that as well. We call it x bar. When we're dealing with a specific set of data, we often use x bar to designate the mean of that data set, comprising all your little x's. And we write x bar equals 2, and that's how we say it. So the question we're asking is, what is the deviation of 1133 from the mean, or x bar, 2? Well, here's our data set, there's our mean, and if we look at all the different gaps or deviations from our mean to our individual data points, we find they are all 1. So the only sensible answer to give for the deviation of this data set is 1. Okay, let's try a bigger set of numbers. What's the deviation of these four numbers from x bar? Well, we know how to work that out. The mean of those numbers is 52, so there's our data set, there's our mean, and here are our deviations. 1, 1, 1, and 1. Oh! We've added 50 to each of the numbers we started off with, but the deviation is still 1. What if we double all our numbers? 2266. What's the deviation of that lot from the mean? Well, this time the mean is 4. So there's our data set, there's our mean, and this time all our deviations are 2. The only sensible answer for the deviation of this lot is 2. As Sherlock Holmes might say, let us consider what we have learned so far and where we may move to next. And what we have determined is as follows. The deviation of the numbers 1, 1, 3, 3 from their mean, x bar, is 1. We have also determined that the deviation of 51, 51, 53, 53 is also 1, and that the deviation is unchanged by adding the same number to each data point. However, when we double all the numbers in the data set, the deviation does change. So adding things to a set of numbers does not change the deviation, multiplying them does. And so, one question remains, my dear Watson. What is the standard deviation? Okay, now we have to go into a bit of formal notation. What's the standard deviation of these numbers from the mean? Here's the formula. It's important that you understand how it works, but you're not going to use it all that often. Here are our x values, 1, 1, 3, and 3. Here's our x bar, 2. Well, that's the same all the way across. Now, I need a formula, so I just need a sum that will work every time to figure out what my standard deviation is. And the sum I'm going to choose is this one. I'm simply going to do each data point x minus x bar. So for the first one, I'm going to do 1 minus 2, which gives me minus 1. 1 minus 2, minus 1, 3 minus 2, and 3 minus 2. When I add together all my deviations, I get 0, which really isn't very helpful. So what I do is I make all the negative ones positive by squaring everything. And when I square all those numbers, I get a bunch of 1s. When I add up the squares of all my deviations, I get 4. Algebraically, what I've done is added up the squares of the deviations from the mean. Now I work out the mean of those squared deviations. And finally, because I did all this squaring to get here, I take a square root. And that, Watson, is the formula for the standard deviation of a set of numbers. Okay, once more with a slightly different set, just to show you it wasn't a fluke. There's my set of numbers. There are my x values. There's my mean. Once again, I work out all my x minus x bars, so 2 minus 4, 2 minus 4, 6 minus 4, 6 minus 4. As ever, they add up to 0, but when I square them all and get a bunch of 4s, they add up to 16. The most important thing is they don't add up to 0. So I add up the squares of my deviations, divide by how many I've got, square root the answer, and get a standard deviation of 2. In fact, we've been working out standard deviation all along. But using our previous method of just kind of looking at the numbers and saying, well, it's obvious, was only really doable when the numbers were incredibly easy. This formula works all the time. So to work out the standard deviation of this set of data, that is the formula. So there's our standard deviation, denoted by the Greek letter sigma. So a standard deviation is a kind of average distance of the data from the mean, and we do a bit of squaring and square rooting along the way to sort out the negative signs. But in reality, when you come to work it out, you don't use that formula. What you use is one of these, or perhaps one of these, or one of these. The point is, you're going to use a pocket calculator. That one on the left is probably the one that's most widely used for GCSEs in England, and it retails at around £12. You're actually making life a bit harder for yourself than you need to if you use that one for level 3 maths. This is a slightly more useful one at core maths or A level. It retails at around £25. And if you don't want to go down the Casio route, there's this one too. And you'll find, as part of the written tasks I've set for after this video, links 2 videos for each of these machines. If you need to find instructions for one of the other calculators in the market, simply type in the name of the calculator type in standard deviation, and do a search on YouTube. But the slight complicating factor is there are actually two versions of standard deviation, and your calculator gives you both of them. For instance, if you use the basic Casio machine and you enter statistics mode, put in your data and go to work out a standard deviation, you'll be given these options. Now, as you can see, there are 4 different values your calculator will give you. The first value, n, that's just the number of things you've got on your data set. Second value, x bar, well, as we now know, that's just short for the mean. But then there are 2 more values it will give you. That one, sigma x, and this one, sx. These are both versions of standard deviation. Now, this one on the left, the one that I've actually told you how to use, this one is called the population standard deviation. And this is the one you use when you've got the data for the entire population in which you're interested. It's possible that if you want to investigate examination results in a school, your population is the school. Therefore, you could conceivably have all the data for that population. However, more often than not, you are dealing with some kind of sample, in which case you use that one, which is called the sample standard deviation. And this is what you use if you're working with a sample of some data set. For instance, if you're looking at heights of men and women in England, then you're not going to go and measure all of them. You will inevitably have a sample, and that's the one you use. In practice, this is the one you use most of the time. This one should be your kind of default setting. Let's just look at what this means in practice, because the numerical difference isn't very great. Let's start off by looking at the standard deviation for the numbers we began with. And as we know, we get the answer 1. That was in fact the population standard deviation. If you put these numbers into your calculator and work out the sample standard deviation, you get approximately 1.15. But what you need to notice is that the sample standard deviation is always a little bit bigger than the population standard deviation. You can think of this as being related to the fact that when you've got a sample, obviously you don't know everything about the data, so you need to make your margin of error, your deviation if you like, a little bit bigger. Sigma x, sx, 2 different measures of standard deviation. If in doubt, use sx. So, to summarise, we now have 3 different averages, the mode, the median and the mean, and now we have another abbreviation for the mean, not mu this time, but x bar. And for our measures of dispersion, for the mode we don't really have one. For the median, we generally use the interquartile range, and sometimes the range, especially when we're drawing box plots. For the mean, we've got the population standard deviation, sigma x, or the sample standard deviation, whereas for the median you often use both measures of dispersion, the interquartile range and the range. If you're working with the mean, you have to choose which standard deviation is appropriate for the setting. Now, download the worksheet, look at the introductory video explaining how to use the particular calculator you will be using for the course, and then attempt the follow-up questions you've been set. And I will speak to you again soon.